Hello, everybody, and welcome to our deep dive on ClickHouse Sharding and Replication. My name is Robert Hodges, and I'll be the presenter today. I'm backed up by the knowledge and expertise of the Altinity engineering team. I'll tell you a little bit more about us in a second. Before I go too deeply into this webinar, I'd like to just discuss a couple things that'll help you have a better time. First, this webinar is being recorded, so we'll send out the link to both the webinar as well as the chat. Excuse me, not the chat, but the slides after the webinar is done. Second thing, we should have time to take questions. You can go ahead and enter them into the question and answer box. This is visible in your in the Zoom control bar. The other thing you can do is you can just post them into the chat. I don't really care. If it's a relevant question as I'm going along, I'll go ahead and answer it. Otherwise, I hope there will be some time at the end, and I can certainly stay later and answer your questions as well. Okay, very quickly, us. So Altinity is a bunch of database geeks, for the most part, at least 2/3 to 3/4 of us. We've all worked with databases for many years and in fact, decades in some cases. I've been working with databases of different kinds since 1983, so it's coming up on 4 decades. My day job is CEO of Altinity, but I'm basically a database person. That's the main focus of my career. The folks that we're talking to, for the most part, your application developers looking to learn about ClickHouse. And in this particular case, what we'd like to do is go ahead and dive deeply into sharding and replication, which is one of the secret powers of ClickHouse and enables great applications. Final thing about Altinity. Altinity is an enterprise service provider for ClickHouse. So we have a ClickHouse cloud offering. About a third of our customers or more run on that. And then we have 150 or so customers who are running things self-managed. These are one of the things that we do at Altinity is we support you no matter where you run ClickHouse. So you can run it in the cloud platform, you can run it yourself. There's also a new offering called Altinity.Cloud Anywhere that allows you to control, own the data, but we manage it for you. We do a lot of open source work, among many other projects, and as well as contributions to ClickHouse itself. We wrote the Kubernetes operator for ClickHouse, which some of you on this call may already use. So a very quick introduction to what ClickHouse is, because we really want to get into the depths here. It's a SQL data warehouse. It is kind of like a combination of MySQL and one of the popular data warehouses like Vertica, which was very popular starting about 20 years ago. So it understands SQL. It runs everywhere, kind of like the portability that you expect with MySQL. ClickHouse will run on everything, literally from an Android phone up to clusters with hundreds of nodes. It has a shared nothing architecture, which means that it basically has attached storage. It organizes its storage into columns. That's a very important point for data warehouses. It's common for practically all analytic databases, major database analytic databases on the market today. We won't talk too much about that, but the basic idea is you can think of every column being stored as essentially as an array. This is not so great for transaction processing because it means there are many files. In ClickHouse's case, normally 2 for each column. So if you have to change something, you have to write to a lot of files. But if you have to read something, it's super efficient because you can just rip down these columns, which then also compress very well, so on and so forth. What we'll be focusing on today in particular is the next 2 things. The fact that we can parallelize across many hosts. Sharding and replication both enable that. Underneath, ClickHouse uses vectorized execution, which means that it's taking those columns, breaking them up into essentially arrays and using various array processing tricks to make the processing run faster. The scaling is excellent. We won't show examples of that today, but with replication and sharding together, you can build clusters that process many petabytes of data. And finally, it's open source. It's Apache 2.0, which is great, that allows you to use it for any business purpose. And as a result of that and all these other properties, it's become really popular as a core engine for real-time analytics. Distributed data, just one this is called a deep dive, but we have to qualify that a little bit. Distributed data is just complicated, and things that seem simple on the surface are very can actually turn out to be quite complex and require a lot of thought. We normally cover this topic in a 2-hour education course, which I'd recommend you sign up if it's actually part of a bigger class on ClickHouse. But even that is just touching the surface. I think of it as analogous to this famous river called the Bolton, or this place called the Bolton Strid. It's a river in Yorkshire. It's this picture, as it shows, indicates it's about 2 meters across. It turns out what's under there is up to 60 meters because there's a bunch of caves and other things underneath. So it's a these are deep waters that we're going into. We're going to try and cover as many of them as possible, but there's still more to learn. And you may have questions. We'll try to answer them, but it's a very deep topic. Let's introduce it. So let's think about scaling, because this is the big reason why typically the reason why you are going to apply sharding in particular, but often replication as well. So ClickHouse nodes are great at scaling vertically, which is to say, replacing whatever machine you're running on with something more powerful. So here's an example where we have some host, it's out in the cloud, it has network attached storage like EBS, if it's running on Amazon, has a certain amount of RAM and a certain amount of CPU. We can increase the capacity of that host very simply just by making it bigger, getting a bigger VM and reattaching the storage. Amazon does this incredibly well. So does Google. So do other clouds. So, for example, you can in a matter of a minute or two, you can scale from having something that has 2 vCPUs all the way up to say 64. The problem is that at some point that's not enough, and so that's where clusters come in, because they introduce what's called horizontal scaling. So instead of having a single instance and making it bigger, kind of like the way you would typically scale something like Postgres, what we're going to do here is we're actually going to break the data up into pieces and then with multiple copies and use that to scale the system. So there's 2 notions that in clusters that are very important. One is shards. So shards you can think of as subsets of the data. Properly speaking, disjoint subsets. So you'll break up, if you have, say, 100 tenants, you might put 33 of them on one host, 33 of them on the next host, and 34 on the last one. They're disjoint. They don't touch each other. Replicas then are copies of the data within each shard. And you can think of the shards as increasing your write capacity, and as well as the sort of the total amount of storage that you can have for storing data. Replicas, on the other hand, and what the shards do technically then is you can think of them as just adding write IOPS. So if you're reading data, or if you're pulling data into the system at 10 million rows per second, it's often convenient to spread this across multiple shards. Say you have 5 shards, each of them takes 2 million a second. Replicas, on the other hand, improve your read IOPS. So your ability to have more people reading more data. They also have the side effect that they're a great HA mechanism. So if one of the replicas dies, you have other ones and your system does not become unavailable to users. But we won't be touching on that too much today. So there are different sharding and replication patterns in ClickHouse, and I'd just like to talk about them a little, because you'll often see these come up. One is to think about having data just sharded without any replication, no copies. And you might think that this is useless. It's kind of like RAID 0 in storage, but it turns out this is actually a very useful pattern to think about in ClickHouse, because you can think about things like the ClickHouse system tables, where you might have many shards. They all have their own copy of the system tables. You might like to run queries across them, all of them simultaneously. Therefore, this all sharded pattern is very useful, because it allows us to treat these as shards and then run queries across all of them at once. Another pattern, which is at the opposite end, is to have tables or to have data completely replicated. We call this all replicated. And so in this case, we might have a table which is just repeated on every replica, no matter where it is and no matter what shard it belongs to. That's handy if you have small amounts of data that need to be universally available. a currency conversion table, for example, which might be something that every shard needs for queries. And so it's just convenient to blast a copy out to all of them. And then finally, for big data or for large tables, they're sharded and replicated. So you're actually breaking up the data set into 2 shards in this example, and then you have 2 copies of each shard. So these patterns will come up again and again, and most sharding that we do tends to be a combination of one or more of these. So the sharding and, well, actually I should say replication is done at the table level in ClickHouse. And in fact, in building these systems, we tend to think of tables being sharded and tables being replicated. We don't think, for example, of databases or entire servers being replicated the way we do on MySQL or Postgres. So you have the basic, the merge tree table, which is the workhorse for ClickHouse. And the merge tree table has a bunch of variants like summing and aggregating merge tree. They're used for aggregation, replacing collapsing merge tree, which handle updates, version collapsing merge tree, yet another one to handle updates. So these are in their plain forms and they don't replicate. If you want to make replicas, you'll have to use the replicated form. So for example, instead of an ordinary merge tree table, you would have replicated merge tree. This table is identical in virtually every ways, or table type is identical in virtually every ways to merge tree. It's just that in addition to all the other things that merge tree does, this one will automatically replicate any data that it receives to other tables. So how does that work? Well, we have a table called on time. This is a well-known airline data set. We define it using replicated merge tree table type, or table engine, as we would say. And we have one copy of it we have one replica on the first server on the left. We have another replica on the server on the right. And what happens is if we insert data into the first node, so node 1, and it lands in this on time table, it will it'll create one or more blocks because of this, or parts, as we say, and those parts will then get eventually replicated to node 2. By eventually, I mean that by default, it doesn't happen instantly, but it will, within a short period of time, the blocks will show up on the other node. So how does that happen? Well, each of the replicated merge tree tables has knows how to connect to Zookeeper or ClickHouse Keeper, which is a ClickHouse native replacement for Zookeeper. And within Zookeeper, there is a list of the tables as well as the contents of those tables, specifically the parts. So when a part is loaded into this first node, the replicated merge tree stores the data, but it also makes a note in Zookeeper. It says, "Hey, I've got this part," and it has it gives the identifying information for it. Meanwhile, the other node is just scanning Zookeeper, keeping an eye on things, waiting for things to show up. As soon as it sees a part, it then goes over and grabs it by default through port 9009 and pulls it onto its table. That's how it works. So as long as you have Zookeeper available, in fact, you must have either Zookeeper or ClickHouse Keeper for this to work. Your tables will happily replicate, and you don't have to do anything to ensure that the data moves between them. So one common question that we get is, well, what exactly is replicated? I mentioned inserts, but there are also other commands that are replicated. So for example, if you do an alter table, that will automatically get replicated. There are things like alter table freeze partition that do not get replicated, but anything that changes the data in the table will go ahead and will be replicated to other copies. Another important command is optimize. So optimize table will get replicated. The reason for this is that it changes the structure of the data, it changes the parts. So that needs to be transferred. That information needs to be transferred to the other nodes. And then finally, truncate. So if you do truncate table foo on one replica, the data will disappear on all replicas. What's non-replicated? Well, actually, your major DDL statements. So create table, for example, and other ones you can read here. There is a way, though, to cause them to happen across the entire cluster, but it doesn't go through the replication mechanism. We'll look at it in just a second. So, so that's the basic background behind this. This may be very familiar to all of you. What I'd now like to do is go ahead and uh, talk about how to build the schema, since the replication is at the table level and we have to pick a replicated table engine. I'm going to show you how to put this together and sort of knit things together so that you can begin sharding and replication. So here's an example of a distributed data set, and it's got shards and it's got replicas. So let me explain what's going on here. This is a data set called On Time. It is airline data from the US Department of Transportation. It's one of our favorite data sets. There's a row in it for every flight, commercial airline flight that happens in the United States. So the data, the actual flight data itself, we're going to store in a replicated table called On Time Local. And what you see here is these two red copies those are replicas. The blue one, and so those are replicas of each other. The blue ones are also replicas, but I use different colors because they're in different shards. So we have two shards and they have two replicas each. It's sometimes useful in queries to look up airport names, which isn't in the on-time data. So we have a fully replicated table called airports that has airport data, including the full name of the airport that the politicians assigned to it, as well as the exact latitude and longitude, stuff like that. And because that's a useful table and not very big, we replicate it across all copies. And then finally, if we'd like to do queries where we're querying the entire set of shards, we have what's called a distributed table. It has no data, but it knows where the underlying shards and replicas are located, and it can send queries off to them. Let's go ahead and dig in and show how this whole thing was set up. So the first thing you do typically is you create your fact table. So that's where your data are. These are the events that you're measuring in the outside world. And as I said, you use the replicated merge tree. So far, if you look at this, the columns are pretty similar to any other merge tree table. There's no difference there, but this replicated merge tree has an important feature, which is this path. And that's the path in Zookeeper or ClickHouse Keeper that it follows to enable it to both communicate as well as learn about parts that it needs to replicate. So you see ClickHouse, and then this thing here is called a macro, where it says cluster. We'll talk about those in a second. These are values that just get filled in. And this means that basically you can run this command on any database or any of your servers, and it will correctly construct the path that it needs to listen on. And then replica here is an additional parameter that's a unique name across all shards and replicas. Again, if you have macros set up, and we'll show you how to do that in a minute, this will all just happen magically every time when you run the command. The rest of it, partitioned and ordered by, is exactly as it is a merge tree. That breaks up the table into pieces and gives a sort order. So the next thing we want to do, once we have those tables holding the actual data, is we want to have a distributed table to actually find things, to allow us to do selects across all the shards. So for this, we create a table called using the distributed engine, and the distributed engine is an umbrella table. And what it does is it just has a name, and it knows which cluster we're using. So this is a collection of shards and replicas. We'll show how that's defined in a second. It knows the database the table is located on, the table name, and then it has something called a sharding key. And a sharding key is used if we're inserting data to help us spray the data evenly across the different replicas. So this is the second thing that you do. One thing I'll point out is if you're doing this regularly, you want to be very careful with the database name. I'm using current database here. This particular command may or may not work with all clients. It works great, for example, with ClickHouse client, which has a notion of a current database. But if you're doing it through APIs, you sometimes just need to give the database name to make sure that ClickHouse doesn't get confused. And then finally, a fully replicated dimension table, pretty simple. Create table if it not exists. Oh, I'm using this as I used that in the previous. I'm actually copying this from another table definition, but again, it uses replicated merge tree, and it uses a pretty similar path. The big difference is that within this first path, we don't make any distinction between the replicas. So there's just one path that all the tables communicate through. And then partition primary key order by partition by tuple, if you haven't seen it, is just an idiomatic way of saying I don't care about table parts because this thing is so small that it'll just make one part. So the one of the things that we wanted to do was dig into how macros are defined. They're used in that path, and there's a file that you set up by convention. It's known as macros.xml. It has a macros tag, and it just has values which are then automatically available when the server that reads this file is running. So you can find out what they are by selecting from the system.macros table. But for our create table commands to run, we need to have cluster shard and replica all defined. So there's a very, very useful command that we can then use, which is called which is our command setting called on cluster. And I mentioned that create table and other DDL don't replicate, but you can send them to all copies or to all servers in the cluster. So for example, if you want to create this table on time local, and we would say something like create table if not exists on cluster, and then this will be filled in with the name of the cluster, the collection of shards and replicas that we're using, and the DDL will just get blasted out to everybody. What's kind of nice, the standard way to do it is to say create table if not exists. That means if the table's already there, you can just go ahead and blast this out, and it will add the table. But if the table already exists, for example, because it's a shard that you're adding new shards, but you have old ones that already exist, the command will just be ignored. So this works for create, drop, and alter table, and is a standard way to set things up and keep your DDL consistent across all the servers. So the next question is, how does it actually know where to go? Well, we had this cluster here, so that's a macro, and it has a name. And what that in our example, that name is going to equate to demo. And what you'll see is there's another file on ClickHouse that's called by convention called remote servers.xml. It's stored in config.d, and it tells what the shards are and what the replicas are. So here are and so the name of the cluster is demo. You have one shard with a couple of replicas. You have another shard, presumably with a couple of replicas, as many as you want. You can use any pattern of these that you want. One really important setting that was added within the last year and a half or so is this secret parameter. This is important because it's a shared secret, and when by default these things won't try to authenticate when they move across between servers. But if you have this shared secret, that will be used to ensure that we authenticate between the servers. They must all possess the same value. And if you use TLS encrypted connections, which I'm not showing you how to do them here, but you can set that up, it will also be hidden. So it gives you secure communications. One of the other advantages is this also allows the user that you're using to be propagated through, so that when you do a distributed query, if you start with a user demo, for example, you'll then use demo when the query is blasted out to other locations. You can find the clusters, or the layouts as they're sometimes called, just by looking at system.clusters. This is pretty important. You might not use this normally, but you often have to debug these if you get them wrong. So it's useful to check the system tables. One thing I should say here, and I'll mention this in at the end of this talk, this is starting to look like a lot of setup to make this work, and it is. It's simple, but if you blow it, screw up any of it, your cluster won't work, and you'll have like weird problems, like a query will work sometimes but not another, and it really depends on where things get load balanced to, because maybe you don't have a macro correctly defined on one of your cluster servers. A way to get around that is to use Kubernetes. So the ClickHouse, I mentioned the Altinity ClickHouse Kubernetes operator. It does all of this configuration automatically, and it does a couple of other convenient things, like when you add shards, it will automatically copy your schema onto it. So all of this setup that we've talked about over the last few minutes is taken care of for you automatically. That's it. If you, as far as schema definition is concerned, you do these, set up these 3 tables. You've basically got a sharded system. What we now want to do is load some data into it and run some queries. So let's go ahead and talk first about data loading, because we have to do that first before we can query anything. So we have 2 ways to get to the data. We can use the distributed table, which knows where the underlying local copies are, or we can insert directly into the local copies. So one of the things that there's often a choice here about how to do it, and there's not really a right answer here, but for example, you could have a data pipeline which is reading off Kafka, and if one way that you can do it is just, you've built a consumer, it reads off the pipeline, it can just turn around straight and post the stuff into the on-time table, which is distributed, and that will automatically split the data out or shard the data and post it out to one of the local copies underneath. The other thing you could do is you could actually just have one of these consumers sitting in front of every server. They read from and Kafka is smart enough that it will distribute the data across, and you can then just have the consumers each applying directly to the underlying replicated tables. This means that your application needs to have some knowledge about how shards are arranged. On the other hand, distributing through the distributed table means you don't have to. Your application doesn't really have to know where the underlying tables are. So the trade-offs are that in going through the distributed table, you may require more resources. Going locally, your applications have to be a little bit brainier about where the data is located. Here's what an insert looks like into a distributed versus a local table. It's the same. That's one of the things that's really cool about this model is you can insert into on-time, that's our distributed table. And you can insert into on-time local. Other than the table name, there's no difference in the syntax. There's no difference in in anything else. There is a difference in what's happening under the covers, and this is important to understand. If you insert into a local table, when ClickHouse comes back and the ClickHouse client comes back, typically that block is just already there and you can go ahead and query it. It's a little bit more complicated in distributed tables. So what will happen is by default, your insert will be taken and it will be broken up into blocks for insertions using the partition key if it's available, and it'll be stuck into a queue. That's basically an on disk. It's just a directory in storage, and there's a thread pool that will be taking those blocks and then propagating them out to the local copies. The point is that when ClickHouse says, hey, got the data, what it really means by default is it's got it in this queue. It hasn't actually reached a table. And there's a couple of settings that you can use to control this. One is called, in insert distributed sync, if you set it to 0, which is the default, it will go ahead and distribute tables asynchronously. This means you could lose data. If this first server that we're going to crashed and that file system got cleared, it doesn't automatically, but if something happened to it, you'd lose those inserts. If you set it to 1, then ClickHouse is not going to come back until you know the copies have actually reached the local tables. So there's a couple of, in summary, there's a couple of options, and 2 I've talked about, and there's a third one, but you can insert to a local table. You can insert to a distributed table. ClickHouse will figure out the sharding, and then using a sharding key that you provide in the table definition. And then there's also other mechanisms using gateways. There's a well-known one called CH proxy. This can sit in front of ClickHouse, and it only works with HTTP connections, but it's smart enough that it can read the blocks or read the SQL and send it directed out automatically to the underlying ClickHouse servers. And then the asynchronous versus synchronous insertions that you get in this model. I've talked about the insert distributed sync, where you're going to a replicated table, or excuse me, to a distributed table. The second thing is ClickHouse also has a setting for Zookeeper or ClickHouse Keeper called insert quorum, as well as select a sequential consistency. These are a couple of settings that allow you to force replicas to sync before you get an answer back. It means your inserts will be slower, but you can guarantee, for example, that they reached a quorum of servers. If you had three replicas, the block would have to reach 2 of them before you'd get an answer back. So that's how we load data. Let's talk about selects. This is what you do most of the time in your applications. So it's kind of a similar idea. So we're going to go ahead and the application is going to connect to one of the to a server and connect to the distributed table, on time in this case. We call the server that it lands on the initiator or the initiator node. What that's going to do is a distributed table is going to look at it's going to parse the query, and then it's going to break it up and send a subquery out to each of the local copies. So we have on-time local, and by default, it will just pick the local. If it has a local copy, it will. The default is to prefer that, or at least it was last time I looked. So we don't have to jump across the network. The other thing is, if there are shards that are not present on this machine, it will go ahead and connect to one of the replicas. On the local tables, it's just a normal select. So, and we'll talk about this innermost sub-select. There's a little bit of distinction about what actually gets sent. But the key thing here, and this is a really important point, if you're going to go, be doing aggregates, which is where most of the expense and time of sort of the computational, the I/O and the compute, if you will, most of that effort is actually in the aggregation process where you're scanning your data. So that's going to be done locally. So that's the basic model. This is sometimes called federated query. Let's look at some actual examples. So here's an example of a query coming into on time, and through the distributed table, it gets parsed. And then what's going to happen is the query down below is going to be sent to one replica each for on time local. So if there are 2 shards, 2 of these copies will be sent. You can see that all it did was it just rewrote the name to on-time local and then picked a couple of replicas to go fetch from. What happens then, and if we go back to the picture, is those queries run, and then as they complete, they stream the results back. Let's see if this has a good example. Yes, it has an order by. Excellent. So what will have to happen is, in order to give you a complete ordering, when the data arrive back on the on the initiator node, we will have to merge the aggregates. So if we're computing averages, we'll have to make sure we've got the, done the full average computation across both copies of data, and we'll have to sort it. So this is what happens in the distributed table when that query comes back. But it's basically a pretty simple idea. So the nice thing about ClickHouse, one of the things I like, is you can see all the pieces. There's no question what's going on. Another interesting bit of behavior is that if you have a join in there, ClickHouse will send that off to the off by default. So for example, here's an example where we're selecting from a default.ontime, that's our distributed table, and we're going to join on default.airports. That is a local table, and remember in the example it was replicated to all copies. We're just going to rewrite the name on-time local, and the whole thing, the whole kit and caboodle, including the join, is going to be sent down. And then query will run, and it will, and you'll get your result back. So this is the default behavior. But if that left side table is a query, there's a subquery. So what I mean by left side table is that's the first query, or the first table in the join. So on time, that's the left side. We have the join, and on the right side is default.airports. So if the left side of the join is a subquery, in fact, that is what gets sent to the remote servers. So if you haven't seen this trick before, you might ask, well, why would you do that? Really simple reason here. If you send the join down, you're going to collect a bunch of data from the airports, the airport name in this particular case. You're just going to drag it along and send it back to the initiator. And then it's all going to, once everything merges, it will collapse down to a much smaller set of rows. In this case, it's simpler just to run the basic aggregation, let that come back to the initiator, and then do your join. And that's what this query does. So, and as you can see, if you're not a, depending on how long you've used ClickHouse, one of the things this shows, ClickHouse is not doing, we're doing a distributed query here. ClickHouse, though, does not have a distributed query optimizer. It's instead rule-based. It's based on what it sees in the SQL, and to decide how to take this query and send it out to the, out to the local copies, and then merge and order the data and hand it back to you. That's a really important point with sharding and replication, because there are much more complicated situations that you can get into with distributed data. And this is where things get kind of deep. So we only had one distributed table here. And in my example, I used a local table name. So the distributed table just says, okay, that's a local table. I can see it. I don't have to do any translation. I'm going to assume that the table is present when it gets to the local, wherever I need it. But let's say you have a case where you have two large tables and they're too big to fit on single shards. In this particular case, you might want to send a distributed query where you're selecting from T1, which is one distributed table, and that is doing a query which is using an in operator, which is effectively a kind of join. And that's from another table, which is also so big that we need to do a distributed query on that as well. So in this case, ClickHouse doesn't really know whether the data is correctly organized in the local copy, so that this join, or in, which is, as I say, a kind of join, so this will really work. And by default, if you try and do this query, ClickHouse will just spit at you and refuse it. It simply won't do it. But there is a setting called distributed product mode that tells ClickHouse, hey, you basically say, hey, I know what I'm doing here, and here's a couple of options that I want to use. So for example, if you say allow, that's one of the settings, it will just do the translation, and then it will send the query down in the form that you see in the middle. And what that will do is when it hits each node, it will go ahead and run another query, which will be distributed. So you'll have to wait for that to finish. You could say local, which is where you say, hey, I know what I'm doing. I know that when this arrives, even though that's a distributed copy, I'm going to find all the data I need to join on. So in that case, we're just going to translate it to the local name. And then there's global, which is saying, hey, I'm going to use a local copy. It's safe to use a local copy, but I'm going to do it on the initiator and send a copy of it out to everybody. So this basically does the query on the distributed table, and then creates a temporary table. That's where a in temp, that's what that means, so that you don't have to redo this distributed query every single time you run it, or on every single node that's getting subqueries. So is this confusing yet? This was the single most confusing thing I've ever learned in ClickHouse, which may mean that I haven't gone deep enough yet, but it is confusing. And this is where you want to be very careful when you're starting to do these kinds of queries. It's really important to think about design. It's also important to know what the heck is going on down there when these queries get sent. Let's talk about what's actually happening. So when you're running these queries, if you have any question about what is actually happening and which queries went to which location, the one of the things you can do is run a query on the system tables, which will and you can use this from cluster. I'll show you exactly how that works in just a minute. What this is a query that runs, looks at the query log table of every server in the cluster and brings back information, and it will allow you to see what was the initial query that hit your initiator, what was the query that got sent to each of the copies. And here's that query run in a real, it's easier to show an example. You can see what I'm doing here is just confirming that, hey, my query, which I ran, see this one right here, there's an initial version of it that hit the, let's see if I've got the right one. Yep, that's it. So 1 means that was the query that came in first. And then these 000s, these are not initial queries. Those are the subqueries that got sent out to different copies. So this is an incredible, a very useful debugging tool to find out exactly what's going on if you're confused about why a query isn't giving what you expect. The second thing, which is maybe the first thing, is you want to think about data when you have large sharded data sets. The simplest way to handle this problem that I've just described about distributed joins is not to have it. And in fact, what is common and very common in ClickHouse is to use what's called the big table model, where you basically have, it's your large table. You have a single large table that gets sharded, and then you have a bunch of small tables that are just replicated everywhere. If that's not possible, if you have 2 large tables and you need to join them, you'll then need to do what's called bucketing. And the idea here is you have a large table on the left, you have a large table on the right. They need to join on these keys ID. So think of this as large left, large right. We then just make sure that the matched keys are present on each of the shards. This is up to you to do it though. ClickHouse doesn't do it magically, and it won't move data to make it happen. I hope that's helpful, but it's a really important point about how to design these systems. I'm going to show some very, very quickly, pass over a couple of quick tricks to query distributed tables. These are super useful table functions. You're building a system, you can only connect to one node at once, but you're in there, you're looking around, you want to see what's going on another node. You can use the remote function. That's a table function. So you can select from it, you give the name of the host, you give the database and the table. It allows you from one server in your cluster to go ask, hey, what's the count on another table? And it has a couple of different versions. You can use a secure connection or an unencrypted one. You can actually insert this way. So this is super useful. I use it mostly for debugging, but there's more. So right here is you can, if you want to know what's going on with your different, underneath with your hosts, you can actually just throw the host name in when you're selecting off a distributed table, and you'll see something like the following, where it gives me my host name and it gives me my counts, but it split them up into pieces. I can make sure, if I want to make sure my counts are consistent and that each table is evenly balanced, this is a really simple way to do it. Now that's just going to look at 2, because it's a distributed table. It's only going to show 1 replica from each shard. If I want to see all shards, I'm 2 by 2 here. I can use the query that's shown below. Remote supports this kind of interesting substitution syntax, and it will go and give you copies from everything. It gets better. So there's also something called cluster. Cluster is kind of like a distributed table that you don't have to define. It has the same arguments, essentially. So you have the name of the cluster and then the database and the table name. And you can go ahead and blast this out. And what it'll do is it'll basically act like a distributed table, but you don't need to define it. The difference between this and using a distributed table is it's less efficient because it has to set up all the network connections. every time it runs, but distributed tables don't do that. But otherwise, it behaves essentially the same. And then cluster all replicas is just going to all replicas in the cluster. Same idea. These are super useful for debugging problems. Particularly, a good example is when you have a slow server, you can often use these to figure out which is the slow one, because you can, you can go ahead and ping them one by one using the remote function, and the one that takes the longest to come back, that's maybe the one that's having problems. Final topic here is scaling up. So we promised we would talk a little bit about performance. Again, a very deep subject, but let me just give you some of the basics. A lot of times when people build these clusters, they start thinking, and they're thinking, hey, I need to build capacity. I need to make sure that I've got, and that I'm allocating the right number of resources to serve my application. They'll start thinking about the cluster as a whole. And that's actually, you'll learn after you've done it a couple of times, that's what you want to start doing, is thinking about the first, like the initial node. And there's a reason for that, because when you initially start using ClickHouse for an application, you don't actually know whether you need to shard. ClickHouse can perfectly easily handle 1 trillion rows of data in a single server if you set things up right. So, if you have less than 1 trillion rows, the null hypothesis is you actually don't need to shard. Now, in fact, many people do, and for good reason. But so what we'll do is, when we're building these systems or helping people build systems, first thing we do is load production data on a single node. So production data, why do we want that? Because it has proper distributions, it has the right size, like something that's a realistic size. And then what you're going to do is take select queries that your application wants to run. You take insert queries that you use to load the data, and you're just going to run those things on it and see how fast it is. And what you're trying to do is max this out so that you can see the maximum capacity on a single node and get that one sized properly. And that'll take a while. So you'll run your queries, you'll see, hey, this query X is slow. You'll either fix the query or fix the data, and then you'll retest. And so you'll cycle around until you're pretty clear what the requirements are. Then what you can do is add replicas, and you can, to increase select capacity, you can sort of go to the next level up and add shards to increase insert capacity. This is a great scheme. It's what Cloudflare uses. A wonderful talk that we'll show at the end from Mick Kosakowski that talked about this and how to do it. One of the key things that you have to do in distributed tables is pick the sharding key. If you're inserting through the, and this is the hardest thing to do in sharding, is to figure out how to split the data between shards. And there's 2 reasons for it. One, it's hard just to begin with. Second thing is, if you don't get it right, ClickHouse won't rebalance the shards for you. Here's a couple examples. So if you have a multi-tenant system, you could just put all the data from all the tenants together in a single system, in a single set of shards, and you'll just use some randomized key, like you'll run city hash. If you're doing a web crawler, run city hash 64 on the URLs that are the URLs that you're running, or that are in your data. Now, if you have a multi-tenant system, it's also tempting to do something like this, to run city hash 64 on the tenant ID. This turns out to be kind of bad, because tenants are of different sizes. Tenants, and so as a result, if you happen to get a big tenant that always lands on shard 2, they're going to have a lot more data there, and it's going to make things really unbalanced. So you can get unbalanced nodes. It's hard to add nodes, because with this scheme, when you add tenants, if you just throw it in, all of a sudden you'd go from having 3 shards to 4 shards. And this formula here would actually send things to the wrong location. So it's kind of tricky. The benefit is that if you do this, the queries can skip shards, because they can recognize, if they know the partition key, which ClickHouse does, it will then skip partitions where it doesn't think there's any data. So this is kind of tricky. So if you pick one of these, particularly the latter, you're going to have a rebalancing problem. And let me just talk about this because ClickHouse doesn't do it automatically. It's not like Cassandra. Uh, so here's three things you can use. You can use ClickHouse Copier, and it basically just does a select off the old tables and moves some fraction of your data over to the new one. There's also an undocumented command called alter table move part, which will move parts, which are pieces of merge tree tables between shards. This is available in the test, but there's no documentation on it. I don't have a strong feeling about how well it works. And then finally, you can move tables parts manually. So you do an alter table freeze partition, you'll rsync the partition over to some new host, attach it, and then just go drop the original partition. So people script this out. What this means is if you don't get this right, it could be kind of painful, particularly as your data set grows large, and ClickHouse at this point doesn't yet help you with it. So for that reason, a lot of older systems sometimes use what's called bi-level sharding. And what this does is it kind of takes both approaches. With the tenant IDs and the URLs, we would actually just have a set of pools of shards where they're just balanced across, using some random value like URL. But in tenant group one, all of the tenants that belong to it have all their data on all of the servers. And you keep those kind of small, and that avoids the situation where for a single tenant, you need to go look at 50 servers. So this is a way to do it. Your application has to know what the pattern is and then pick the right pool to go to for a particular tenant. But that's usually not very hard. It just means like have a table somewhere that tells where the tenants are. Got an extra slide here. What this really should say is that's it. So just a couple of notes. Where's the documentation? These are the usual suspects, ClickHouse official docs, the Altinity.blog. We talk about this a lot. This talk is going up on the Altinity YouTube channel. There's a lot of stuff. We do have the Altinity knowledge base. If you don't know about it, is a really valuable resource. We have hundreds of customers, and every time we see something interesting, we'll just stick it in the knowledge base. It's Apache licensed. You can go out and search it. So for example, if you're thinking about going to ClickHouse Keeper, we have some thoughts there on whether that's how stable that is and how to manage it. There is this most excellent talk which Mick Kosakowski of Cloudflare did a couple of years ago. That's basically the capacity planning loop that I described. This is how Cloudflare does it. It's if you're building big systems, it's great to look at his approach. And then there's lots of other places to find. There's meetups, blogs, talks, things like that. And just to get direct help, usual suspects. So the ClickHouse channel, there's actually two, one in Russian, one in English. Then there's public workspaces. There's a ClickHouse public workspace, the Altinity public workspace. And then if you want to go deeper in this and get more help, we do education. So we have an 8-hour course on this that includes distributed systems, but distributed data and sharding and replication, but goes very deep on other things as well. And then of course we have support and Altinity.cloud, which does all of this stuff automatically. So that's it. This is a pretty deep topic. This may not have covered all of your questions. I would be delighted if you have questions about this. I'd be delighted to stick around and answer anything that you have. Otherwise, I'd like to thank you for listening to this presentation and wish you good luck. This is a very powerful capability of ClickHouse. When you use it well, you're going to produce really, really fast and cost-efficient results. So with that, I'll take questions if people want to queue them up. Okay, not seeing any questions yet. I'll wait for another minute. If you have something that you're you're looking at and want to ask, I'll hold for another 60 seconds. Otherwise, thank you, and we hope to talk to you soon. Lots of ways to contact us. We love this topic and would be delighted to talk about it with any of you. So, oh, you want to work at, so Oleg, I shouldn't have said your name. Somebody who wants to work at Altinity, it could be that we want you. So please, if you haven't done so already, we have a careers page. Look at, we have a bunch of positions we're opening. We're looking for, if you thought this was an interesting talk and you want to do this for a living, or you thought that I did a bad job and you could do it better, please send us, please do apply. We'd love to have, love to talk to you. Great. Well, I don't see any questions coming. Oh, here, you mentioned that. Oh, here we go. Okay, so you mentioned that. Oh, here's a wonderful question. Thank you so much. This is where I never know how far to go deep. You mentioned that the replicating tables increases the select capability in terms of the concurrency, or it could increase the performance in your queries. It actually turns out it's both. So originally, ClickHouse could only go to one copy per replica, but since then, there is a feature, and I have not used it, but ClickHouse now has the ability to actually use to distribute the queries across the same replicas. And I think the trick that it probably uses, I've never used it, and I don't know how it's implemented, or never used it intentionally, is that ClickHouse knows what the parts are and can basically make sure that the queries only look at certain parts on certain replicas. But the idea here is that if you had two replicas, yes, in the best case, it could speed up your query, ideally by 2x. So because you'd split it across replicas. This is a new feature, and I'm pretty sure that knowing ClickHouse, there's a setting for it. You have to tell ClickHouse it's safe to do this. It's something you can look up, but there is that capability. Good. I don't see any other questions. So I'm going to go ahead and call this good. Thank you all so much. It's a pleasure to do this, and we hope to talk to you soon. Have a great day.